It's okay. Okay, can we take seats, please? Right, so this morning I'm going to talk about forces in this talk, and then we'll talk about putting it all together in the next one. Let me just start with gravity, seeing as particle physics tends to ignore gravity, but sometimes you can't. But let me show you why it is. The three forces that we tend to deal with are electromagnetic, weak, and strong. Now, the electrostatic force, you know, in hydrogen is an inverse square law, and gravity is also an inverse square law. And so to give an idea of how feeble gravity is, you could ask the electron and the proton in hydrogen, they have an electrostatic potential energy, and they have also a gravitational potential energy between their masses. And the ratio of those two potential energies is 10 to the minus 40. Which is a small number, and to give you an idea of how small it is, if you took the size of a single proton, 10 to the minus 15 meters, and compared it to the size of the observable universe, which is about 10 to the 26 meters, that is about 10 to the 40, 10 to the 41 orders of magnitude. So if you can imagine a single proton compared to the whole observable universe, that is like the strength of gravity compared to electromagnetic forces between individual particles. Therefore, we ignore them. Between individual particles. Of course, gravity has the property of adding up. The more particles you have, the more the gravitational force is. And there are some places where it reveals some unusual things, not just in falling apples, but in the problem of dark matter. So let me just show you the background to this. If you've got a large mass like the Sun, with smaller masses like planets going around it, then you know Newton's inverse square law tells you the force between them. And you equate that with mv squared over r, and you can work out what the velocity profile of those objects is as a function of distance. And you find that the speed will drop like the square root of r. So the outer planets are moving slower than the inner ones. And that is indeed what happens to the planets. But if you look at some spiral galaxies, where you can measure the relative speeds of the stars by the Doppler shift of their spectral light, you find that in those, there's clearly a lot of mass in the middle, and there's these stars on the outside, but the velocity profile seems to be roughly independent of distance rather than dying away. There's large error bars on this, and it varies from one galaxy to another, but overall, you get this impression that the outer stars are not following the rules. And you've got one of two opportunities. Either you say this shows that on these distance scales, Newton's law is not correct, and you can play that game, but it's very difficult to convince you fit it with other data. Or that there's more stuff there giving gravitational forces than you are actually seeing in your telescopes. And that is what's given rise to the idea of dark matter, namely stuff that does not shine in electromagnetic radiation of any wavelength, but gives a gravitational force which affects the motion of the stars and galaxies. And it turns out when you do the sums that you need the dominant stuff in the universe to be this dark stuff that is unseen. So that's an observation from cosmology. The nature of the dark matter is a big puzzle, and one of the possibilities at the LHC is that we will discover new particles called supersymmetric particles which have perhaps the properties of dark matter, and I'll mention that later on. But that, if it's true, would be a wonderful synthesis between particle physics and cosmology. So what is it? We know that whatever it consists of has to be electrically neutral, and there's two sort of scenarios called hot dark matter and cold dark matter. Hot meaning moving relativistically. For example, if neutrinos had about, a small mass, it's possible that they collectively, because they wouldn't shine, they don't feel electromagnetic forces, they've got no electric charge, but their gravity could add up and outweigh everything. It turns out when you do the detailed sums, that doesn't seem to work. The other extreme is cold dark matter, very massive electrically neutral objects, and that is what Susie might provide us with, and we'll talk about that in the next lecture. So that's all I'm going to say about gravity. I now want to talk about the strong and then the electromagnetic and weak forces. So the strong force, which we met, I guess, first of all, students between the protons and neutrons that binds together nuclei, we now know is a remnant of a deeper force acting on the quarks inside those protons and neutrons. And I'm now going to show you how that force works and show you how similar it is, in principle, with the good old electromagnetic force. So the idea is that quarks, in addition to carrying electric charge, carry another form of charge, which we call colour. To give it a name, and I'll tell you why in a moment. And the rules of attractions and repulsions between colour charges are the same as you meet between electric charges. So, for example, quarks carry positive colour charges, and whereas electric charge comes in only one variety, it's plus a number or minus a number, this blue charge comes in three varieties, and just to give them a name, we call it red, yellow and green, or red, yellow and blue colour. Three different colour possibilities for quarks, positive, and antiquarks will have three colours, negative. And then you apply the familiar... Then you... Is there somebody that can turn this thing down? Thanks. Then you apply the rules that you're used to in electrostatics, where the rules are like charges repel, unlike charges attract. So like colours repel, unlike colours attract, and see what happens. So the simplest possibility is to take a positive colour and a negative colour, just like you're used to in electrostatics, and they will attract and cancel out, and that gives you a quark and an antiquark, a meson, one of the families of hadrons that we met yesterday. The novel feature with colour, because there are three different colours, means that there are now some other possibilities for attractions that you don't see in simple electrostatics, but you do here. Suppose we've got two positive red-coloured quarks. Well, like colours repel. But two different coloured charges, red and yellow, unlike colours, attract. And if you've got three different quarks, each with a different colour charge, three different colours can attract. Now bring a fourth quark along. We don't know why it is, but nature, for some reason, only has three varieties of colour charge. So the fourth quark must have the same colour charge as one that is already there. So in this particular picture, the yellow quark will be repelled by the yellow quark that was already there. It will, however, be attracted to the red and the blue. And it turns out, when you do the sums, the strength of attraction to the red and blue exactly counterbalances the repulsion to the yellow. So this group of three is, if you like, colour neutral. So this quark is sort of left hanging, wanting to know what to do. And it goes and looks for two more quarks with different colours so it can bind with them. So depending upon whether these quarks are flavours ups or downs will determine whether you end up with neutrons or protons, but all flavours come in these three colours, and it's the colours that are forcing the quarks to attract one another. So if there was two ups and a down on the left there and two downs and an up on the right, you've got a deuteron. So that's how the two things have come about. So now you can see the beginnings of an analogy between colour charges and electric charges. Electric charges, attractions of opposites, build up atoms. Colour charges build up the baryons. And just as atoms which contain electric charge can then build up molecules, so baryons which contain colour charge can build up nuclei. So in this analogy, nuclei are the colour analogues of molecules. Now, in the case of electric charges, we also have for many years known how to write down a relativistic quantum field theory called quantum electrodynamics. By complete analogy, you can do the same with colour charge, and you get quantum chromodynamics, QCD. And QED describes the interactions between electric charges and photons. QCD describes the interaction of colour charges and gluons. Photons are massless, spin-one quantum bundles of electromagnetic radiation. Gluons are massless, spin-one bundles of colour radiation. So the analogy is complete. The only difference is, at this point, there is one variety of electric charge, plus or minus. There are three varieties of colour charge, plus or minus. So now let's look at the simple sort of diagram in QED to describe an electron scattering from an electron by exchanging a photon. And then see the analogy with QCD. So the idea in QED, Feynman 60 years ago produced this sort of beautiful code for keeping track of all the mathematics, drawing these diagrams. The lines in these diagrams represent mathematical expressions, and you would actually meet those in the formal lectures. But we theorists still use these diagrams because they're a very convenient way of helping you visualize what is happening. You can almost see one electron bouncing off another here, for example. And the role of the photon is to transfer energy and momentum from this electron to that electron. And hence this electron feels a force. So we visualize in QED the exchange of these what's called virtual photons as transmitting a force from one side to the other. So the electromagnetic force is transmitted by the exchange of these particles, photons. And when you write down the Feynman rules to calculate the chance of these things happening, there are various factors, but one of them is at the junction where the photon meets the electric charge, we put E, which the square of E divided by 4 pi, we call alpha, is 1 over 137. It's a measure of the sort of probability for these things to happen. It's the price you pay every time an electric charge emits a further photon. You're adding this extra penalty. The reason that's a nice thing in practice because it means that you don't need to worry about very complicated diagrams. Every time you add another photon, you're being penalized by another factor of 100. So maybe this is the simplest diagram and it's a very good approximation, and that's called perturbation theory. But here, the simplest diagram, there's an E squared over 4 pi, which is 1 over 137. Now let's go to the analogous thing for quarks carrying colour charge, exchanging a gluon. Exactly the same words apply. The difference now is instead of E, the electric charge, being the scale, it's G, the colour charge, magnitude setting the scale. And it turns out that G squared over 4 pi is about a tenth. We call this not alpha, but alpha subscript S for alpha strong. Now, there may be a government health warning on this at the moment, but I will reveal in about 3 or 4 minutes, when I say a tenth here, there's a little bit of iffiness to this, but we will see what I mean by that in a moment. But that is essentially the only difference at this stage. Yeah, there's the government health warning. Okay. The reason for the health warning is that you can't always ignore the higher diagrams. For example, going back to QED, there's the possibility that the photon was being exchanged, but during a brief interval, the electron emitted a photon which turned into an electron and a positron and came back again. That's a virtual process which is not allowed if energy is conserved, but in the quantum world you can violate energy conservation for very short periods of time. So diagrams like this exist and can be calculated, and the effect of these is that the higher the momentum that's exchanged between these two electrons, the more important these quantum corrections become. And the effect of them is that what we call alpha, 1 over 137, isn't actually a fixed number. It turns out that the effective strength depends upon how much momentum is being exchanged. So this 1 over 137 is the value when the momentum exchange goes to 0. It turns out that in QED would predict that the value of alpha would slowly increase at higher and higher momentum. And indeed it does. Experimentally, in experiments that were done at LEP, producing the Z boson, which we will talk about shortly, at 90 GeV momentum exchange, alpha had grown to 1 over 128. So alpha, the effective coupling strength, depends upon the amount of momentum being exchanged, or if you like, the amount of momentum you are probing the thing with, the amount of resolution you are looking at it with. And in the first lecture I was saying how momentum, the higher the momentum, the shorter the wavelengths of your probe, the better the resolution you have. The effect is that the higher the momentum you probe with, the more you resolve these quantum effects, that you never see a single electron. You see it surrounded by virtual electrons and positrons and photons and so forth. And the harder you look, the more you see that. And the manifestation of it is that what you think of as alpha being a number is actually a momentum-dependent quantity. It grows slightly with energy. Same remarks hold true for QCD, with a very subtle difference. Just like QED, there are diagrams at the top there where a gluon turns into a quark and an antiquark and comes back again. But this is where the profound difference suddenly emerges. The fact that in QED there is only one variety of charge is ultimately the reason why the photon has no charge. In QCD, the fact that the quarks have 3 colour charges means there is the possibility that a red quark might radiate a gluon and turn into a blue quark, with the gluon carrying off the colour. So the fact that there are 3 colours for the quarks means that the gluons themselves carry the colour charge. And hence gluons can attract gluons and make weird things called glue balls, which people look for. But in particular, it means that there is another possibility at that little top vertex that the gluon, instead of turning into a quark and an antiquark, could turn into a pair of gluons and back again. And when you take all this into account, you find that in QCD, that the effective strength, which you call G, instead of rising slowly with energy, falls with energy. So as you go to very high energies, very high momentum, very short distance probes, QCD's value of G gets smaller and smaller. And so you can do perturbation theory in QCD just like you do in QED. And that's called perturbative QCD, and the fact that QCD is like that in practice means that you can analyze high energy experiments, or technically large momentum transfer experiments, very precisely using the techniques of perturbation theory in QCD. So the analogy then is almost complete. QED, alpha is very small, you use perturbation theory, you can calculate things and experimentally verify them to 12 places of decimals. So in that sense, QED is indeed correct. QCD, at very short distances, very high momentum, you can use perturbation theory. Alpha is small, but not that small. You use perturbation theory, but there are subtle techniques that you have to do to get around the fact that alpha isn't quite that small. But it nonetheless is very precise for high energies, and so precise that one can, with confidence, make predictions about how they should go about doing the experiments at the LHC. The ability to do experiments at the LHC is based in part upon the belief that we understand the innards of the proton in terms of its quarks and gluons well enough at those extreme energies that we can work out the implications of how to go and look for things. Of course, the problem with QCD is that when you come to the low energy end, the coupling strength is getting bigger and bigger. And as you come to distances of about 1 Fermi, the strength is going off to infinity. The interaction between the quarks becomes very strong. In fact, so strong that nobody has ever been able to pull an individual quark out of a proton. In fact, we believe, and there's pretty good theoretical indications, that quarks and colour charges are permanently confined inside these clusters about 1 Fermi in size that we call hadrons. And there's a lot of activity going to trying to calculate the properties of those hadrons in the strong interaction regime. And you need special techniques to do that. And people set up quantum chromodynamics imagining that space and time is a discrete continuum. They call it a lattice, and you do numerical simulations on a computer. And there may or may not be lectures about lattice QCD in these lectures, I don't know, but if there are, that's what it's all about. So these Feynman diagrams of the electromagnetic interaction, let me now say a little bit more about them so we can then see how they link with the weak interaction. So far we've seen a very nice similarity between the way that electromagnetic interaction works and deep down how the colour, ultimately the strong interaction, works. Very similar. So here's the Feynman diagram for an electron scattering off a quark, say, and you can turn these things around and imagine them being an electron and a positron annihilating through a photon turning into a quark and an antiquark. Analogously, I could have a quark and an antiquark annihilating through a photon and turning into a quark and an antiquark, or through a gluon. The diagram is the same, it's just the lines represent different particles. But the rules are the same. For the photon case, put E squared. For the gluon case, put G squared. Now come to the weak force. And at first sight, this is totally different. And at second sight, we will see that this also is playing the same game. So the weak force first appeared in physics back in 1934, when beta decay was first being observed, a neutron turning into a proton, emitting an electron and a neutrino. And it was Fermi who made the first model of this. He assumed that the neutron, the proton, the electron and the neutrino all sort of came out at the same point. I'll put it there as a black box. And he wrote down the quantum mechanical amplitude for this and worked out from that the rate that the beta decay should happen. And to get the answers right, it turned out that he needed to have a scale overall, and this scale is known as the Fermi constant. Big G with a subscript F for Fermi, and its magnitude is 10 to the minus 5 inverse GeV squared. And the fact that 10 to the minus 5 is a much smaller number than 1 over 137 is the historical reason why the weak force became known as the weak force. It was that much weaker. This was purely empirical by Fermi in 1934. There was no theory behind it. It was just the empirical fact 10 to the minus 5 is small, hence we call it the weak force. If you're looking very carefully, though, you might already notice there's a catch here. That I've talked about alpha being 1 over 137, which is a number, whereas GF is a number with a dimension. So I'm not comparing similar things, but they didn't think about that at the time. Let's see the implication. Now, move the thing forward 60, 70 years, and we can look inside that black box. And you find that it isn't all happening at a point. What is actually happening is that that black box involves the exchange of a W boson. And even better, we see that deep down, it's not the whole neutron playing the game, it's a single quark inside the neutron that is emitting this W boson, which then turns into the electron and the neutrino. And the theory of this was developed in the 50s and 60s, and it turned out that the theory also implied that there would have to be a neutral analogue of the W boson, which became known as the Z0, Z for 0, 0 for 0. And these things were experimentally discovered in the 1980s. So you're beginning to see here that even the weak force now is following the same sort of rules. That there is a spin 1, that's the W, the spin 1 boson transmitting the force. The difference, though, this time is the following. The photon and the gluon are massless spin 1 bosons, whereas the W boson has got a mass that is about 80 times bigger than a proton. And, of course, you might say, well, how can a proton with a mass of about 1 GeV and a neutron with about 1 GeV emit something with 80 GeV? I mean, that can't happen. Well, of course, it can't happen if you're conserving energy momentum, but in the quantum world, for a very brief time, you can borrow that. But, of course, the act of borrowing 80 times your own mass is very short-lived, and that is why the effect of this turns out to be very feeble qualitatively. I will now show you quantitatively what is going on. So I'm now going to do part 2 of what I will call the Electroweak story, how the electromagnetic force and the weak force indeed come together to reveal that what we've been calling the weak force for 70 years is nothing more than the electromagnetic force but in disguise. So let's take this history. So I suppose the history of unification goes back as far as 1864, when Maxwell first united electricity and magnetism into what we call electromagnetism. Then 100 years later, it was Glashow, Salam and Weinberg who proposed that the electromagnetic and the weak forces could be united into what we call the electroweak force. This uniting being based upon the idea that there are W bosons, the analogues of photons, with this one little problem: the W bosons have to have mass, and the photons don't. But the trick involved the Higgs mechanism, which was a way of starting off as if the W bosons had no mass at all, playing this trick, and they gain a mass without spawning any of the nice features in the story. The technical details of that you'll meet later, but let me just for the moment take on board the fact that W's and Z's were expected to have a mass, and I will tell you very shortly how big that mass is and why the numbers work out beautifully. And it was 1983-84 that the W and Z particles were found in experiments here at CERN by colliding protons and antiprotons. A single quark in a proton and an antiquark in an antiproton, if they just by chance had the right energy and the right combination of flavors, they could once in a blue moon produce a W or a Z rather than the many, many showers of pions that they normally produce. So it was like looking for a needle in a haystack, but eventually it was done, and Rubier and Van der Meer got the Nobel Prize for the discovery, which actually was quite interesting given that the Nobel Prize for the theory had already been given even though these things hadn't been found. So if it had turned out all to be wrong, whether the Nobel Committee would have asked their first prize back again, but that's speculation. So having discovered the W and the Z in these sort of rather clumsy experiments with the protons, let me say what I mean by that, because it's quite relevant to the present stage in history with the LHC starting. Protons and antiprotons, they're complicated things. They contain quarks. I said yesterday 3 quarks. Well, that's actually the simplest way of making them. The more resolution you look at these things with, of course, you don't see a single quark. You see it surrounded by a cloud of quarks, antiquarks, and gluons. So the proton is actually 3 quarks and a cloud of quarks, antiquarks, and gluons. It's a real messy bag of stuff. And the antiproton likewise. But you use them in your first experiments because it's the easiest way to get to high energies. The fact that these things are 2,000 times more massive than an electron or positron means that you pack a lot of punch. So you can access new regions that you've never been to before, but in a rather clumsy way. Having discovered things, in the case of 1980s, the W and Z, you can then go to very clean probes like electrons and positrons. Because an electron and a positron are nothing more than an electron and a positron. And you can control their energy precisely and tune the energy of the collision to exactly what you want. And that was what was done in the 1990s here at LEP, the Large Electron-Positron Collider. And it was tuned specifically to collide at 90 GeV, because at that energy, the Z boson exists. And they accumulated about 10 million examples of producing Z bosons and seeing how it decayed, and looked at it very precisely. And in the course of about 6 years of experimentation, they found that indeed the Z is unstable. And it decays, when I say democratically, it decays into all possible things that it could do. In particular, it can decay into neutrinos. A neutrino of the electron type and its antiversion, a neutrino of the muon type and its antiversion, a neutrino of the tau type and its antiversion, and a neutrino of any other types that we haven't previously seen and their antiversion, so long as they're light enough. Now, you can begin to see qualitatively here, the more varieties of neutrino that there might be in nature, the more opportunities there are for the Z to decay. It's like a bucket full of water. The more holes there are in it, the quicker the water drains out. The more channels for the decay of the Z there are, the shorter it will live. And what was found remarkably is that the Z indeed is unstable. It has a width, and this manifests itself in the following way, that you collide the electron and positron, not exactly at 90 GeV, but sometimes at energies below, through 90 and over, and you see that the cross-section, the probability for something to happen, rises and falls. And that rise and fall is what we call the Z boson resonance. Now, in quantum mechanics, the width of this thing is like the uncertainty in energy over which this thing is produced. And quantum mechanics, the Heisenberg uncertainty principle, tells you that an uncertainty in energy multiplied by an uncertainty in time is of the order of Planck's constant, which here I've written down as 6 times 10 to the minus 25 GeV times seconds. So by measuring the width of this bump, you can work out how long the particle that made it lives. And from that you find that the Z boson lives for about 10 to the minus 25 seconds, incredibly small time. But what is more beautiful is that you can span very precisely over the peak, and the data points are the black dots, and the 3 lines are what theory would expect for the width of the Z if there were only 2 varieties of neutrino, which of course we know is nonsense, 3 or 4. and the line for 3 neutrinos goes beautifully through those data. So it is the precise measurements of the properties of the Z in the 1990s which showed that there are at most 3 varieties of light neutrino. I mean, if there's another variety of neutrino that weighs more than half the mass of the Z, like 50 GeV, then of course you wouldn't know that. But if there is, that's something totally different. That we know there are at most 3 varieties of light neutrino. Given that each neutrino seems to be married to a negatively charged lepton, like an electron, muon or tau, we infer at most 3 varieties of charged leptons. Seeing that each pair of these seems to be married with a pair of quarks, up and down, charm and strange, top and bottom, we infer that if this system is indeed right, there are at most 3 generations of these quarks. That might all turn out to be wrong, but that is how it appears to be, and why it is we don't know. But this is to show that this is an experimentally deduced fact that we had from LEP by studying the Z precisely. And then from 96 to 2000, they did electron-positron annihilation at higher energies in the hope, well, in fact, in the success of producing pairs of W bosons, charged W plus and W minus to conserve electric charge, electron and positron coming in, W plus and W minus have to balance going out, and you need much more energy to produce those. And so they studied with quite a lot of detail the properties of Zs and Ws for many years. And so from that, the whole precision of the Electroweak was confirmed. So now, what's this got to do with unity? And this is what I now want to show you, the idea of the weak force being electromagnetism in disguise. And it all goes back to this point that when Fermi came into the game, the Fermi constant is not a number, it's a dimensional quantity, 10 to the minus 5 divided by dimensions of GeV all squared. And we now know that it's not a black box, it is a W boson being exchanged. Just like in electromagnetic interactions, it's not a black box, it's a photon being exchanged. And we've seen already in the electromagnetic case that alpha is 1 over 137. That is a number because, well, it's a number, and the weak strength is much smaller in GeV squared. So why are the dimensions in one case not in the other? And there's a slight government health warning here, but I'll tell you what it is. It's not anything to panic about. The quantum rules that Feynman's diagrams take account of are many, but the one that you need to know for this is, what does the wiggly line actually mean mathematically? When you write down the quantum amplitude, which is the thing that ultimately determines the probability that this happens, when you write down the quantum amplitude, the rule is that you write down the strength, the E squared, or the alpha, and then if the amount of energy in this photon is E, you write 1 over E squared. The government health warning is this: technically you write 4 vectors squared, but I'm just doing it with energy squared by choosing a particular frame. Okay. The point will be made clear, I hope. So alpha over E squared is the mathematical expression for the electromagnetic case. Suppose that a Z boson, which is electrically neutral but weighs in at 90 GeV, I'll call that mass m subscript Z, suppose that that was exchanged with the very same strength as electromagnetism, namely alpha. The rules would be alpha divided by E squared, and because it's got a mass, you have to add m squared. So the full Feynman rules are E squared plus m squared for the things that are being exchanged. In the case of a photon, m is nothing, that's why it's just E squared. In the case of a Z boson, m is mz, so it's E squared plus mz squared. But let's pretend for a moment that alpha is the same for both of them. And now let's see what happens. If I do an experiment at very high energies, meaning energies much, much bigger than 90 GeV, E squared will be huge compared to mz squared, and so I can ignore the mz squared. And in those extreme cases, you will see I've got an identical expression, alpha over E squared for the electromagnetic case, alpha over E squared for the Z case. In that situation, they would be identical. But now let's come down to energies, very low energies, like we were stuck with in beta decay. There, the energy involved is only an MeV, negligible compared with the mass of the Z or the W. In that case,
I could ignore the E squared and approximate the thing as alpha over mz squared. Now you begin to see, of course, if that is a black box, alpha over mz squared is a number divided by gv squared. And Fermi told us that that was 10 to the minus 5 divided by gv squared. So in the Fermi model that didn't know there was this thing being transmitted, he said, oh, 10 to the minus 5 over gv squared. Well, I can write 10 to the minus 5 over gv squared as alpha over 28 gv all squared. So in fact, you would now suddenly have, if the case was that the Z and the W's masses were of the order of 28 or 30 GeV, the strength of the interaction would be exactly the same as we observe. So I'm saying that badly. If their masses were around 28 or 30 GeV, what we call the weak force would actually be the very same strength as the electromagnetic force, but apparently weaker because of this 30 GeV object that was transmitting the stuff. So at this stage you would say, fine, but why then is the Z mass not 30 GeV? Why is it 90 GeV? Well, the answer is that there is a bit of government health warning here. The things that I've ignored are the following. When you do it more precisely, you find there's a square root of 2 that you have to take into account. The weak interactions violate parity. Left and right asymmetry is a property of weak interactions. That also enters the maths of things. And when you do the thing all carefully in detail, 28 GeV turns out to be 80 GeV, and the Z about 90 GeV. And within the errors of the theory back in 1980, that was bang on what turned out. Today, one can even do quantum corrections to the theory and compare with the more precise measurements that one has for the Z and the W. And it remarkably works in the case of everything. So the bottom line is that actually the electromagnetic force and the weak force follow the same rules. There are spin 1 bosons that transmit both of them. The strength of the Z and W vertices is the same as the strength of the electromagnetic vertices. The difference is that the W and Z are massive, which means that at low energies their effects appear feeble, and it became known as the weak force. But it is that mass that makes it appear different from electromagnetism. In a sense, it's electromagnetism in disguise. Of course, it begs the question, why do the W and Z have mass and the photon not? That is a question still to be solved. But that is the state we're at. So, why do we care, other than being interested in theory and experimenting things? Well, it does matter. So let me bring this lecture towards its end by saying what goes on at the heart of the sun that gives rise to the energy that enables us to be here. So and we'll see how the weak interaction plays a critical role in this, not just the fact that it is there, but the strength of it. The first stage in the burning of the sun, 2 protons, the seeds of hydrogen, come together. One of those protons undergoes inverse beta decay, turning into a neutron, a positron, and a neutrino, the neutron then combining with the proton to make a deuteron. So the first stage is 2 protons make a deuteron, a positron, and a neutrino. This deuteron finds itself in the centre of the sun where there's lots of protons around, and proton and deuteron can make a nucleus of helium-3, and that's happening all the time. 2 nuclei of helium-3 can bump into each other and make a nucleus of helium-4, liberating 2 protons. And the end result of this whole chain is that 4 protons have ended up as a nucleus of helium-4, 2 positrons and 2 neutrinos. So that is what's going on in the sun. The sun is turning hydrogen, protons, into helium, emitting positrons and neutrinos. The positrons are annihilated by electrons that are in the plasma in the sun into 2 gamma rays. The gamma rays then spend about 100,000 years bouncing around, getting to the surface, by which time their energy has degraded enough that they emerge, in particular as visible light. The neutrinos can escape and be detected in underground detectors. And so that is what is going on, and we now know quantitatively by the number of neutrinos arriving, now that we understand that there are indeed 3 varieties of neutrino, and beginning to get the hints of these oscillations that they can change from one to another. The numbers remarkably balanced. We can look into the heart of the sun and see quantitatively that it works precisely as we thought it did. I think that's quite remarkable. You can do experiments on Earth to look inside a star and see quantitatively how stars work. So this now is no longer conjecture. This is indeed experimentally established fact. The first stage is very slow. Once it's happened, the next two stages happen almost instantaneously. If you were a single proton in the sun, there's only a 50% chance that in the last 5 billion years you would yet have bumped into another proton. In other words, the sun is only halfway through the first stage of its burning cycle. And it is the weak interaction that is controlling this first step because of the beta decay that you see there. So the proton turning into a neutron, emitting the positron and neutrino, is an example of the weak interaction controlled by the W boson. The fact that the weak interaction is weak is why this process is slow. The fact that this process is slow means that enough time has elapsed for intelligent life to arrive and appreciate the fact. The next two stages involve the strong interaction and are very fast. So, the weak force is feeble in the sun because 10 million degrees, which is the temperature in the heart of the sun, in energy terms, from our very first lecture, is about 1 keV, and 1 keV is utterly negligible compared with 80 GeV. And that is ultimately the reason why in the sun that first stage is a weak, feeble stage, while the sun has stayed active long enough for us to have evolved. So we exist because the mass of the W is not zero. So mass matters, which begs the question, so why is there mass? And I'm not going to answer that in the next question. You'll get that in the later lectures, but I'll give you some examples of how symmetry emerges and disappears. But I will say one thing so that the confusion does get removed. You often see written in popular press that the Higgs boson is the cause of our mass, and that is not true. The Higgs boson, we believe, gives rise to the mass of the fundamental particles like the electron, the muon, the W, the Z, and the quarks. Now, the quarks' masses are just maybe 1 or 2 MeV. You say, well, how do 3 quarks with masses of 1 or 2 MeV end up making a proton with a mass of 940 MeV? The answer is because this colour force confines the quarks. As I said, you try to pull them apart and it stops them escaping, that they're trapped inside a 1 Fermi-sized prism. Now, if you go back to college and do a very simple quantum mechanics calculation, imagine a flat bottom potential with infinitely high sides. And, of course, you will see that the waves have to fit. They have to have nodes to fit in there. So to make your first thing with the nodes in it, you have to have an energy. So the fact that if you confine a little lightweight quark inside 1 Fermi, it must have an energy of about 300 MeV. And put 3 of them together. So the mass of the proton is given because of the confinement of quarks. If the quarks had no mass at all, but were confined, that would give the mass of the proton. And our mass is pretty much driven by the protons and neutrons in the atomic nuclei. The electrons are only about 1/2000th part of it. So the Higgs gives rise to the masses of the electrons, which gives rise to the size and structure of atoms. So the fact that there is structure and atoms is, we believe, linked to the Higgs mechanism. But the fact that we have mass is due to the confinement of the quarks, which may or may not have anything to do with the Higgs mechanism. So that is where we're currently at. So I will be back in a quarter of an hour. Thanks.